Tonight, we'll be exploring the most extreme thing any human being has ever attempted. The moment we leave Earth and travel into space, everything we depend on disappears. There is no air to breathe and no ground to stand on. No weather, no sound, no life. Space does not care if we survive, yet we choose to go anyway. We build rockets that burn hotter than stars and train astronauts to do the impossible. Against all odds, we keep the human body alive in places where biology begins to fail. Space travel is not safe, natural, or easy. It is bold. It is terrifying. And it is the only way forward if we want to see what lies beyond. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your mind soften and your breathing slow, and allow yourself to float gently into rest. Let's begin. Spacesuits are tiny personal spaceships. A spacesuit is much more than clothing. It is a one-person spacecraft built to keep a fragile human alive in a realm where there is no air to breathe, no pressure to hold the body together, and temperatures that can swing hundreds of degrees in minutes. Inside, every layer serves a purpose. The inner lining wicks away sweat. The pressure garment hugs the body to prevent blood from boiling in the vacuum of space. The outer shell protects against razor-sharp dust and tiny meteoroids. The helmet visor contains a thin layer of real gold to reflect harsh sunlight. Oxygen tanks are fitted into the backpack, along with a carbon dioxide removal system, fans, and cooling water that circulates through hidden tubes. A single tear in the fabric could be fatal, so every stitch is inspected again and again. To leave the shelter of a spaceship or space station, an astronaut must trust this portable world completely. It is a tiny bubble of Earth, carried into the silence of the infinite night. Astronauts grow taller in space. In the absence of gravity, the spine is no longer held down by the body's weight. The vertebrae gently separate, stretching the spinal column by as much as several centimeters. This temporary height gain can feel incredible at first, like a long, slow stretch after a lifetime of hunching. But the effect comes with pain. Back muscles must adjust to their new length, and astronauts often experience discomfort or spasms during their first days in orbit. The increased height also slightly changes how the body moves in a pressurized suit or narrow sleeping bag. Once the astronaut returns to Earth, gravity takes hold again, and the spine gradually compresses back to its original shape. The sudden reversal can also be uncomfortable. Mission doctors study these changes closely because they reveal how space affects the skeleton, cartilage, and connective tissue. If humans ever build cities on Mars or large rotating habitats in space, understanding how the body adapts to different levels of gravity will be essential for long-term health. Space has a smell, and astronauts can describe it. No one can breathe in space, so it may seem impossible that it has a smell. Yet astronauts returning from spacewalks often report a distinct aroma clinging to their suits and tools. Some say it resembles hot metal. Others compare it to burnt steak or welding fumes. The smell is created when high-energy particles from the sun and cosmic radiation interact with the spacecraft's hull, creating reactive molecules that mix with the oxygen inside once the airlock is opened. These particles never reach the human nose directly, but they leave chemical traces on surfaces exposed to the vacuum. Researchers are studying these effects to better understand how to protect sensitive equipment from long-term exposure. The scent of space is one of the few sensory bridges between Earth and the void, a reminder that even in silence, the universe leaves its mark. Your body stops losing bone almost immediately in microgravity. On Earth, bones stay strong because gravity constantly pulls against them. In space, that pull disappears, and the body reduces the minerals it normally sends to strengthen the skeleton. Astronauts can lose close to 1% of bone mass per month in orbit, which is far faster than the most severe cases of osteoporosis on Earth. Weight-bearing bones like the femur and spine weaken first. Calcium that once fortified bone tissue enters the bloodstream, eventually leaving the body through urine. This mineral shift can also strain the kidneys. To counteract the effect, astronauts exercise for hours every day using special machines that simulate resistance in zero gravity. Even so, some loss is unavoidable. Once back on Earth, it can take years for bone mass to fully return, and not every astronaut recovers completely. Learning how to prevent this weakening is one of the greatest challenges facing future missions to Mars, where travelers might spend years away from home. The Sun looks completely different when you are outside Earth's atmosphere. From Earth, the Sun appears soft and yellow because the planet's atmosphere scatters the most intense light. In space, the Sun is a fierce white sphere, blinding and sharp-edged against perfect black. There is no sky to filter its glare, no air to turn sunlight into soft colors at dawn or dusk. Its heat arrives with no warning, and without protection it can burn through metal, fabric, or skin in moments. Shadows in space are equally extreme, pure darkness with no gentle fading at the edges. This stark contrast affects how astronauts see depth and distance. It also changes how solar panels absorb energy and how cameras record images. Every space mission must plan around this raw light. It powers spacecraft, threatens electronics, and creates a constant hazard for unshielded humans. The Sun in space is a reminder that Earth protects us in ways we rarely notice, wrapping us in a layer of atmosphere that softens the violence of starlight. Astronaut food must be safe for zero gravity. Food in space cannot crumble, leak, or spoil. A single crumb drifting into a ventilation fan can cause a system failure. A drop of soup could float into a control panel. To avoid these dangers, every meal is engineered with care. Tortillas replace bread because they do not shed flakes. Drinks are stored in sealed pouches and sipped through straws. Fruits and vegetables are irradiated to kill bacteria. Even salt and pepper must be dissolved in water so they do not fly away. Texture and flavor also change in orbit, so spices are often stronger than they would be on Earth. A blocked nose and shift in blood flow can dull an astronaut's sense of taste, making food seem bland unless it has extra heat or sweetness. There are no ovens or refrigerators, only warmers and vacuum-sealed trays. Cooking is less of an art and more of a form of engineering. Each dish is a miniature science experiment, designed to nourish without taking risks. Sleeping in space requires strapping yourself down. There is no bed, no mattress, and no gravity to pull the body onto a surface. Instead, astronauts sleep inside padded, cocoon-like bags attached to the wall or ceiling of the spacecraft. Without restraints, their bodies would drift aimlessly, bumping into equipment or other sleeping crew members. The sensation of weightlessness can confuse the brain during dreams, creating illusions of floating or falling. Some astronauts describe the experience as peaceful, while others struggle to rest without the familiar pressure of lying down. Lights are dimmed, but noise is always present. Fans, pumps, and occasional creaks from temperature changes in the metal hull. The sleep schedule must match Earth time, even though the spacecraft may see a sunrise every 90 minutes. Learning to sleep in this environment is a skill that takes days, even weeks, to master. Space travel demands rest, but it offers none of the comforts we take for granted. Tears do not fall in space, they clump. Crying is different without gravity. Instead of running down the cheeks, tears form floating blobs that cling to the eyes, building up in a stinging pool that can blur vision. Even wiping them away is difficult, because a cloth will just spread the moisture into smaller spheres. Tears can drift into the nose or cause irritation if they get trapped beneath a contact lens. The only way to clear them is to blink repeatedly until surface tension breaks and the moisture floats free. Emotional moments, allergies, and even dust from equipment can trigger tears. The strange behavior of liquids in space is one of the first experiments children try to imagine, and astronauts live it every day. The human body evolved for gravity. In space, even the simple act of crying becomes a reminder of how far from home we truly are. Spacewalks are one of the most dangerous things astronauts do. When an astronaut leaves the safety of an airlock and steps into the open void, every danger becomes real. One tiny tear in the suit could mean death in seconds. Temperatures can swing from blistering heat to freezing cold as the body moves in and out of sunlight. The slightest force can send a person drifting away from the spacecraft, so every move is anchored by tethers. Even breathing is risky, because the suit's atmosphere must be perfectly balanced to avoid oxygen toxicity or carbon dioxide buildup. Tools must be carefully secured, and every motion rehearsed again and again in underwater training tanks on Earth. Despite all the preparation, spacewalks always carry unknowns. The silence that surrounds an astronaut during a spacewalk is not peaceful. It is the silence of a place where life does not belong. There is no up or down in space, and the brain must adjust. In microgravity, the inner ear loses the sense of balance that helps people stand and walk. The brain, suddenly cut off from this steady flow of information, must build a new way to understand orientation. Walls, floors, and ceilings have no meaning, so astronauts often feel disoriented or upside down even when floating upright. Some adapt quickly. Others experience confusion, nausea, or dizziness for days. Simple tasks like reaching for a toolbox or turning a corner inside a spacecraft can become mental puzzles until the mind reorganizes itself. Objects no longer fall when dropped. Muscles no longer stabilize the body automatically. Every movement must be relearned with care. This shifting sense of reality is one of the most profound psychological challenges of life in orbit. Learning to let go of gravity does not just change how the body moves, it changes how the mind feels at home in the world. Space radiation can damage DNA. Outside the protective blanket of Earth's magnetic field, the human body is constantly bombarded by cosmic rays, solar particles, and high-energy atoms traveling at incredible speeds. These particles can pass through skin, tissue, and even metal, slicing through the DNA inside cells and leaving behind broken strands or mutations. On Earth, our atmosphere shields us from most of this danger, but in space, astronauts receive radiation doses far above the levels considered safe for long-term health. The damage can lead to increased cancer risk weakened immune function, and even clouding of the eyes. Engineers are developing better shielding for future spacecraft and habitats, but protecting the human body from invisible particles that arrive from every direction is a complex challenge. Space radiation is one of the biggest barriers to deep space missions. Every day in orbit reveals more about a danger that follows astronauts wherever they go. Even simple fires behave strangely in zero gravity. A flame on Earth flickers upward, shaped by rising hot air and falling cool air. In space, there is no upward or downward motion because there is no gravity. Flames burn as ghostly blue spheres, floating in place and consuming oxygen slowly and evenly. Without buoyancy, smoke does not rise, it simply accumulates in confused clouds. Fires burn less intensely, but can be harder to detect and extinguish. A small flame in a corner of a spacecraft can silently fill a room with toxic gases before alarms even register the change. For this reason, every material on board, from insulation to electronic wires, must be tested for how it reacts to fire in zero gravity. Fire drills are designed to teach astronauts how to seal hatches, shut off ventilation, and locate extinguishers in darkness and confusion. Fire on Earth is dangerous, but fire in space is an unpredictable enemy that moves in all directions at once. Astronauts must exercise every day to stay alive. The muscles and bones of the body rely on gravity tugging at them constantly. Remove this force, and the body begins to weaken astonishingly fast. Without exercise, an astronaut's leg muscles can shrink, heart strength can decrease, and the ability to stand or even breathe comfortably back on Earth can vanish. To fight this, astronauts engage in daily workouts that last several hours, using machines that create artificial resistance. One machine pulls against the body with elastic cords to mimic weightlifting. Another uses spinning cycles and tethers to simulate running. These workouts are not optional. They are as essential as eating or sleeping. Scientists continue to study how to keep the body strong for missions that could last several years. Otherwise, the first humans to walk on Mars might arrive too weak to stand. Metal can fuse together in space without heat. On Earth, metal objects rarely merge unless they are melted or carefully welded. In space, bare metal surfaces can bond instantly through a process called cold welding. Without any oxygen or moisture acting as a barrier, atoms from one metal object can slide into place against another, creating a seamless join. This effect can occur with tools, spacecraft parts, or even tiny fragments of debris. Engineers must coat or paint metal surfaces that might accidentally touch, or they risk equipment becoming stuck together permanently. This invisible force is not only fascinating, it is important. Without protective layers, a robotic arm might seize, a satellite panel might fail to unfold, or a hatch might refuse to open. Cold welding is a reminder that in the vacuum of space, natural rules change, and even simple contact becomes a science of its own. Microgravity changes how we taste food. Food that tastes rich and savory on Earth can seem dull or faint in orbit. The shift is partly physical. Without gravity, fluids pool in the upper body, creating a constant sensation of being slightly congested. This reduces smell and taste sensitivity. At the same time, the brain recalibrates its senses, adjusting to a world where the body feels suspended. To cope, astronauts often crave bold flavors, spicy sauces, tangy fruit drinks, and foods with intense aroma. Classic comfort dishes sometimes taste bland or muted, while unexpected favorites, like shrimp cocktail with extra horseradish, become highly requested. This shift in taste is not just about pleasure. It is connected to appetite, nutrition, and morale. Long missions require food that nourishes both body and spirit, so space menus are carefully tested to work with altered senses. In orbit, even a simple bite carries the science of human adaptation. Space sickness is like seasickness, but worse. The human balance system is built to interpret gravity, motion, and body position. Remove gravity, and the brain receives strange and conflicting signals. Eyes see a stable environment, but the inner ear senses freefall. This mismatch can cause nausea, vomiting, dizziness, and disorientation. Space sickness strikes many astronauts during their first days in orbit, sometimes making it hard to work, eat, or even sit comfortably. Medical teams prepare for this with medication, careful meal planning, and slow introduction to physical tasks. Eventually, the brain adapts, but the early period can be unpleasant enough to ground missions temporarily. Returning to Earth can trigger a second wave of sickness as the body readjusts to weight and balance. Space sickness is a reminder that even when we leave the planet, we carry a body built for Earth. You can see shooting stars inside a spaceship. When tiny particles of dust or micrometeorites strike the exterior of a spacecraft at terrifying speeds, they release a burst of energy that can create glowing streaks of light visible from inside. Astronauts sometimes witness these flashes while looking through darkened windows or even when resting in dim corners of the station. These shooting stars are not harmless. Each one is a collision happening faster than any bullet. They carve microscopic craters into glass and aluminum, slowly wearing down the spacecraft's shell. Missions track regions of heavy debris and adjust their paths to avoid the densest fields. Yet the phenomenon is humbling. Even within the walls of a spacecraft, humans remain connected to the cosmos, watching sparks of ancient dust ignite against their fragile metal shelter. Growing plants in space is hard, but not impossible. Plants evolved under gravity, with roots that grow downward and stems that reach upward toward the sun. In microgravity, these directional cues disappear. Water does not settle into soil. Air pockets do not rise. Seeds may sprout in unpredictable directions. Yet with careful design, astronauts have learned to grow lettuce, radishes, and even flowering plants in orbit. Special chambers provide artificial light, nutrients delivered through mist or gel, and fans to move air around the leaves. Growing plants is more than a scientific curiosity. It is a test for future colonies on the Moon or Mars, where humans must produce fresh food and recycle oxygen. Watching a seed sprout among the stars provides both nourishment and hope, reminding astronauts that life does not belong only to Earth. Your blood moves differently in space. On Earth, gravity pulls blood into the lower body, and the heart works steadily to pump it back up. In space, blood floats evenly through veins and arteries, accumulating in the chest and head. Faces appear puffy. Legs become thinner. Blood pressure changes, and the heart does not need to work as hard. Over time, the heart itself can begin to shrink, losing muscle mass that must be rebuilt after landing. Doctors monitor circulation constantly and study how to prevent dangerous clotting or low-pressure fainting when astronauts return to gravity. This shift in blood flow affects everything from vision to temperature regulation. It might seem invisible, but every heartbeat becomes a story of adaptation. There is no such thing as absolute silence in a spacecraft. Space itself is silent, but the inside of a spacecraft is never quiet. Fans move air through filters. Computers hum. Pumps and valves click and whir. The constant vibration and airflow are necessary for life support, yet they create a soundscape that never fades. Astronauts must sleep, work, and think within this ongoing mechanical murmur. Over time, the noise can become a kind of background comfort, a reminder that the systems keeping everyone alive are still running. But when an unexpected sound is heard, like a new rattle or tone, it can cause instant alarm. Silence inside a spacecraft is not peaceful. It is terrifying, because it may mean something has stopped working. The rhythm of machines becomes a heartbeat for the crew, marking time in a world without wind or birdsong. Some viruses become more infectious in space. In the strange and shifting environment of space, even microscopic life changes its behavior. Scientists discovered this when samples of viruses, including herpes and Epstein-Barr, were sent to orbit as part of medical studies. In the absence of gravity, under constant radiation exposure, and without the familiar pressures of Earth, some viruses become more active. Their genetic instructions can shift, making them replicate faster or reactivate from dormancy. Astronauts with no symptoms on Earth have sometimes shown signs of viral reactivation in space. This happens even when their immune systems appear normal by Earth standards. Space stress, altered sleep cycles, and fluid shifting in the body all weaken the ability to fight infection. This discovery has serious implications for future missions that may last months or years. Understanding how microbes change in space is crucial to keeping humans healthy far from home. In the end, even the smallest organisms remind us how deeply Earth's environment supports life in ways we barely notice. We use floating water bubbles to wash in space. Taking a shower in space is impossible because water does not fall. Instead, it forms drifting globes that can float around a room like tiny liquid planets. To stay clean, astronauts squeeze small amounts of water or Uranus soap onto their skin and gently wipe with towels. Shower-style devices were tested in early missions, but they sent droplets flying into wires and fans. Even hair washing is a choreography. Water is massaged into the scalp and absorbed back into a cloth or allowed to evaporate into the air filters. Every drop must be reclaimed because water is far too precious to waste. This careful routine is not just about hygiene, it is about comfort, identity, and sanity during long missions. Simple acts like washing the face or brushing the teeth take on new weight when every molecule matters and the body floats in a world of recycled air. Cleanliness becomes a practice in adaptation. The moon's dust could destroy a spacesuit. Lunar dust is not like the soft, rounded grains of beach sand on Earth. It is sharp, jagged, and formed by billions of years of meteor impacts, with no wind or water to wear it down. When it sticks to a spacesuit, it works its way into fabric and joints, damaging seals and scratching visors. During the Apollo missions, astronauts returned to their lander covered in dust that smelled like burnt gunpowder. It irritated their lungs, clogged filters, and clung to every surface. Future moon missions will last far longer, which means dust must be managed on every suit, tool, and habitat before airlocks are opened. Engineers are designing special coatings and electrostatic systems that might repel dust or shake it loose. Lunar dust may seem harmless, but it is a silent, ever-present threat ready to tear through the suits that protect human life in a place with no air to breathe. Haircuts in space require vacuum cleaners. In microgravity, hair does not fall to the floor. Every snip produces strands that drift through the air, some finding their way into eyes, lungs, or delicate instruments. To prevent this, astronauts use special clippers with powerful vacuums attached, sucking cut hair into a sealed container before it can escape. The process is slow and awkward, especially in the confined quarters of a spacecraft. Mirrors are mounted on walls, but every tool must be tethered to prevent it from floating away. Even with precautions, stray hairs sometimes appear, caught in corners or drifting like tiny comets. Grooming in space is not a luxury, it is a necessity. Feeling clean and cared for helps maintain mental health in a stressful environment, and even the ritual of a haircut becomes a small reclaiming of normal life. It is one more reminder of how basic moments become extraordinary once we leave Earth behind. Astronaut gloves make every task harder. A spacesuit glove is a marvel of engineering, with layers that protect against vacuum, thermal extremes, radiation, and micrometeorite impacts. But those same layers make the fingers stiff and clumsy. Fine motor work, like turning bolts or adjusting wires during spacewalks, can feel like threading a needle while wearing thick winter mittens. The gloves must also maintain internal pressure, which makes them push back against every movement. Hours of gripping and manipulating tools can leave astronauts with bruised nails, blisters, or even lasting joint pain. Engineers are constantly working to improve flexibility and dexterity, experimenting with new materials and pressure systems. Every gain in comfort and control makes spacewalks safer and more efficient. But the core challenge remains. Space is not built for hands. Every time an astronaut reaches out into the void, the gloves become a reminder of the fragile human body inside. We have lost tools in space, and they become tiny satellites. During spacewalks, astronauts work with hundreds of items: wrenches, cameras, clamps, tethers, and more. Despite careful planning, a few tools slip away, escaping into open space. Once free, they do not fall. They become tiny satellites, orbiting Earth until they eventually burn up in the atmosphere. One astronaut famously lost a full tool bag, which drifted for months and could be tracked with binoculars from the ground. These objects are harmless on their own, but space is already filled with debris from past missions, old satellites, and fragments from collisions. Each stray object travels at tremendous speeds and could puncture a spacecraft if it crosses the wrong path. Every mission today adds to a growing cloud of human-made space junk. Even the lost screwdriver can become a threat. Space is big, but orbits are crowded. Keeping track of every object, no matter how small, is a constant challenge for mission control and the future of exploration. Every breath on Mars will have to be manufactured. Mars has an atmosphere, but it is almost entirely made of carbon dioxide with only traces of oxygen. The air is so thin that even with a full breath, the lungs would take in almost no usable gas. For humans to live there, every molecule of oxygen must be produced using machines that split carbon dioxide or pull resources from frozen water beneath the soil. These systems must run constantly without fail, and they must do so in an environment that freezes pipes, clogs filters with dust, and pummels equipment with radiation. Future Mars habitats will need backup systems, emergency stores, and repair materials to handle inevitable breakdowns. Plants may someday help with oxygen production, but they will not be enough on their own. On Mars, Breathing becomes a technology, not a birthright. Every inhale would be a triumph of science over nature. The first human to set foot on Mars may never return to Earth. A journey to Mars takes many months, and once there, the planet's gravity, radiation, and distance create challenges that go far beyond existing return technology. The rocket fuel needed to launch from the Martian surface must either be brought from Earth, taking up impossible amounts of space, or manufactured on the planet using local resources. Even then, the journey home would take just as long. Some mission plans suggest that the first explorers may stay permanently, building habitats, growing food, and becoming the first settlers on another world. Returning home after years of low gravity and radiation exposure might be physically devastating. Bones, muscles, and organs could struggle to readapt. The decision to go to Mars might be a one-way choice, not because we cannot bring someone back, but because they would not survive the process. Mars may someday become a new cradle of humanity, but it may require pioneers willing to stay forever. Rocket fuel burns faster in space. On Earth, rocket engines fight against the pull of gravity and the resistance of the atmosphere. In space, with no air and no drag, they can burn more efficiently and reach higher speeds in shorter bursts. But this efficiency comes with risk. Without air, flames behave differently, and fuel must be mixed with its own source of oxygen to ignite. If anything goes wrong, the explosion has nowhere to vent. Every burn must be calculated with precision, adjusting the spacecraft's path by fractions of a degree to reach distant targets. Spaceflight becomes a delicate dance between power and control. Each ignition is a moment of commitment, sending a fragile craft hurtling through a vacuum that offers no chance to stop or slow down. The faster rockets burn, the more exact the math must be. There is no margin for error when the stars are the only road. Spacecraft must withstand temperatures hotter than lava and colder than Antarctica. In sunlight, a spacecraft can heat to temperatures that melt metal. In shadow, it can freeze solid in minutes. There is no air to carry heat away or keep it in, only the raw emptiness of space absorbing or reflecting energy. To survive, spacecraft are built with thermal blankets, layered insulation, and radiators that can channel heat away like artificial skin. Electronics must stay within narrow temperature ranges, or they fail. Water must not freeze or boil in its pipes. Even the spacecraft's orbit can determine its temperature, as it moves into and out of sunlight dozens of times a day. These swings are violent, but the materials are designed to expand, contract, and endure. Every mission begins with an engineering battle against a universe that does not care whether metal cracks or a circuit overheats. Space is a place of extremes, and every machine we send must be ready to face both fire and ice without pause. Mars' sunsets are blue. On Earth, the atmosphere scatters sunlight in such a way that the sky turns blue and sunsets glow orange and red. On Mars, the opposite happens. The thin Martian air is filled with fine dust made of iron-rich minerals. These particles scatter the red wavelengths of sunlight away and allow the blue wavelengths to slip through more directly. As the sun dips toward the horizon, the sky around it fades into a soft blue halo, while the rest of the sky stretches into warm tones of butterscotch and rose. Because the atmosphere is so thin, the colors are subtle, almost dreamlike, like a watercolor painted by a quiet universe. Future astronauts may one day stand on Martian soil and watch these gentle blue sunsets, knowing they are seeing a sky no human eyes ever witnessed before the space age. It is a vision that reminds us how different worlds can be, and yet how beautiful every corner of the cosmos is, each in its own strange and silent way. Space junk is one of the biggest threats to space travel. Earth's orbit is filled with abandoned satellites, fragments from old rockets, paint chips knocked loose during collisions, and even lost tools from spacewalks. These pieces are moving at incredible speeds, faster than rifle bullets, and each one is a potential disaster waiting to happen. A tiny shard of metal the size of a grain of sand can puncture a spacesuit or shatter a spacecraft window. Larger chunks could destroy entire vehicles. The more objects that collide, the more debris they create, leading to a growing chain reaction that scientists fear could someday trap us on Earth. This phenomenon, called a debris cascade, would make some orbits unusable and turn others into deadly fields of shrapnel. To protect astronauts and equipment, space agencies track thousands of objects in real time, adjusting missions to dodge incoming fragments. Engineers are designing new methods of cleanup, but the problem grows faster than the solutions. Space is vast, but orbits are not. Every launch adds to the risk, and every mission must navigate a sky that grows more crowded each year. Astronauts train underwater to prepare for space. A massive pool called the Neutral Buoyancy Laboratory sits near Houston, filled with millions of liters of water and containing a full underwater mock-up of the International Space Station. Here, astronauts don spacesuits weighted just right to mimic the sensation of weightlessness. Every movement is slow and deliberate. A single kick or push can send a body drifting off course, just like in orbit. The water resists motion but also supports the astronaut's weight, providing the closest simulation of working in zero gravity without leaving Earth. Underwater trainers rehearse every bolt turn, every panel connection, and every emergency response. It is a grueling, hours-long workout that leaves muscles shaking and minds sharpened. The pool is not just practice, it is preparation for life in an environment where dropping a tool means losing it forever, and where even simple tasks can feel like solving puzzles in slow motion. The underwater world becomes a doorway to the stars. Time passes differently in orbit. Einstein predicted that time is affected by motion and gravity, and space missions have proven him right. Astronauts aboard the International Space Station orbit Earth at incredible speeds, experiencing slightly less gravity than on the ground. Because of this, time for them moves just the tiniest bit faster. They age a fraction of a second less than people on Earth during their missions. The difference is small, nearly impossible to notice in a human lifetime, but measurable with precise clocks. If we ever send humans to the far reaches of the solar system or beyond, the effect will grow stronger. A traveler journeying for decades at near-light speeds would return younger than those left behind. Time itself bends and stretches as we move through space. The universe is not a single clock ticking steadily, but a collection of rhythms shaped by motion, mass, and gravity. Every orbit is a lesson in physics and a reminder that our senses do not always match reality. Cosmic rays can create light flashes in astronauts' eyes. Some astronauts, while resting in dark spacecraft cabins, have reported seeing flashes of light, even with their eyes closed. These phantom sparks are caused by cosmic rays, high-energy particles from distant stars, supernova, and black holes that travel across the universe at speeds approaching light. When these particles pass through the body, they sometimes strike the retina or optical nerves, triggering flashes or streaks of brightness that seem to appear out of nowhere. The effect can happen at random and makes sleep in space more unusual than on Earth. Scientists study this strange phenomenon to understand how radiation affects the human body and brain. If future explorers travel to places with even higher radiation exposure, like the moons of Jupiter or deep interstellar space, these brief sparks may become constant companions. The universe sends reminders of its hidden forces, even in the darkness behind closed eyes. Our bones could turn fragile on a long Mars mission. A journey to Mars could take more than a year each way, followed by months spent living on a planet with weaker gravity than Earth. During that time, astronauts' bones would steadily lose density, sometimes at a rate faster than any disease on Earth. Without gravity pulling down, cells that normally strengthen bone tissue begin to shut down. Minerals are carried away into the bloodstream and eventually leave the body. Even with daily exercise, the loss is only partially slowed. Once back on Earth, recovering bone strength can take years, and complete recovery is not guaranteed. If settlers remain on Mars permanently, their bones may adapt to the weaker gravity, growing lighter and more brittle over generations. The challenge of bone loss is one of the greatest medical barriers to deep space travel. It forces us to rethink not just how we move through space, but how we build bodies that can thrive in places far removed from Earth's familiar pull. Every tool on a spaceship needs a tether. A wrench, a pen, a toothbrush, or a camera. In space, every object floats freely the moment it leaves a hand. A lost tool can drift into a vent, block an air filter, or hover unnoticed until it collides with something important. During spacewalks, the danger is greater. A single tool escaping an astronaut's grasp can travel forever in orbit, becoming a piece of space debris. To prevent chaos, every object is clipped to a suit, a wall, or a looped cable. Tools are labeled, docked, catalogued, and counted. There is no such thing as casually setting something down. Living in microgravity means relearning how to interact with every object we use. A floating screwdriver is a reminder that space is not built for human habits. The world must be tied down, one item at a time. Space toilets use air instead of water. Without gravity, water does not fall, and waste does not settle. That means a traditional toilet cannot work in space. Instead, astronauts rely on systems that use airflow to gently pull waste away from the body and into sealed containers. Solid waste is compressed and often stored for eventual disposal during re-entry. Liquid waste can be purified and recycled into drinking water through complex filtration. It is a process that must be constant, reliable, and carefully managed, because a malfunction would create a disaster in the limited space of a spacecraft. Using the toilet in orbit requires training, patience, and accuracy. Every part of the system must be cleaned and maintained. In space, even the private moments of life become exercises in engineering and adaptation. It is not glamorous, but it is essential for survival. Solar storms can endanger every mission. The sun does not always shine steadily. Sometimes it erupts with massive bursts of energetic particles called solar storms. These storms can blast through space at incredible speeds, striking spacecraft and planets with dangerous radiation. On Earth, our magnetic field protects us from most of this energy, but astronauts are vulnerable. During a strong solar storm, radiation levels inside a spacecraft could exceed safe limits within hours. Crews must quickly move into shielded areas, often constructed around water tanks or food supplies, which provide extra protection. Electronics are also at risk, since high-energy particles can short-circuit circuits and damage navigation systems. Plans for missions to the Moon or Mars must include emergency shelters and warning systems to predict when solar storms are coming. The Sun gives life to our world, yet it also holds the power to threaten us as we explore beyond it. You can run around the Moon's entire horizon in minutes. The Moon is smaller and less massive than Earth, which gives it a weaker gravitational pull and a much shorter circumference. A person wearing a spacesuit with enough practice and stamina could run fast enough to complete a full circuit of the Moon's visible horizon in just a few minutes. Each step would send the runner bounding in slow, high arcs due to the low gravity. The horizon would seem strangely close, curving more dramatically than on Earth. With each leap, the black sky would loom above, filled with stars even at midday. It would not be an easy run, since the uneven terrain and bulky suit add challenges, but imagining the feat reveals just how different the Moon is compared to the world we know. It reminds us that every place in space holds new ways of moving, seeing, and experiencing reality. Even a run becomes something wondrous. Spaceships must carry their own atmosphere. Unlike Earth, where air surrounds us effortlessly, a spaceship must bring every breath along for the journey. The atmosphere inside a spacecraft is carefully engineered, a balanced mix of nitrogen and oxygen that mimics Earth's air. Carbon dioxide scrubbers constantly remove exhaled gas before it reaches toxic levels. Humidity must be controlled so water does not collect on surfaces and short out electronics. Even temperature and pressure must be tracked carefully, because a single leak could cause the air to escape into the vacuum of space. Every system that supports the atmosphere has backups, and even those backups have emergency modes. Astronauts also carry emergency oxygen masks and suits in case of sudden depressurization. When future missions build habitats on the Moon or Mars, these artificial atmospheres will grow into entire indoor worlds, complete with weather, seasons, and airlocks like gateways between Earth and alien dash. Landscapes. The air within a spacecraft is not a given. It is a fragile gift that we must build, protect, and renew every moment we are far from home. The International Space Station never stops falling. It may look like the International Space Station is floating, but it is actually falling toward Earth at all times. It stays aloft because it moves forward fast enough that as it falls, the planet curves away beneath it. This creates a state of continuous freefall, which we call orbit. Inside, astronauts feel weightless because they are falling too, always missing the ground. There is no sense of acceleration, only a gentle drift that makes everything float. To stay in place and avoid crashing, the space station periodically fires booster engines or receives pushes from visiting spacecraft. Without these adjustments, the thin upper edge of Earth's atmosphere would gradually slow it down. This constant fall reveals a deeper truth about space. Gravity is everywhere, even far above the clouds. Orbit is not the absence of gravity, it is the art of falling forever while racing around the world at incredible speed. You can smell the Milky Way through a telescope. Some telescopes do not just see light, they detect radio waves and chemical signatures from clouds of gas and dust between the stars. Among these signals are molecules like ethyl formate, the same compound that gives raspberries their scent. Other clouds contain signatures of alcohol, carbon rings, and even organic molecules that might form the building blocks of life. By translating these signals into sensory forms like smell, Scientists can get a glimpse of what our galaxy might be like if we could walk among its clouds. The Milky Way is filled with everything from bitter molecules formed in dying stars to sweet compounds floating near newborn suns. These smells are never breathed directly, but they hint at the strange chemistry of the universe and the shared ingredients between distant nebulae and life on Earth. Astronomy, in this way, becomes all of science combined, not just a view, but an invitation to taste, touch, and smell the cosmos through the tools we build. Time dilation could affect future deep space travelers. Time is not the same for everyone. According to Einstein, the faster you move, or the stronger the gravity around you, the slower time passes. Astronauts aboard the International Space Station age slightly less than people on Earth because of their speed and the weaker gravity at their altitude. The effect is tiny, fractions of a second over months, but it is real and measurable. Imagine future humans traveling close to the speed of light toward distant stars. Time for them might pass slowly, while decades or even centuries slip by on Earth. They could return to find entire generations gone. This idea is not just science fiction, it is written into the laws of physics. The universe keeps time as a flexible thread, stretching and contracting depending on the journey. Deep space travel may someday turn time itself into a landscape humans must learn to navigate. Astronauts relearn to walk after coming home. After months spent in microgravity, the human body forgets how to balance, how to carry weight, and even how to coordinate simple steps. Bones become lighter, muscles shrink, and nerves lose practice sending the right signals. When astronauts return to Earth, they often struggle just to stand. Their legs feel heavy and unsteady. Their blood rushes downward in ways it has not for months, making them dizzy. Doctors and trainers work with each returning astronaut to rebuild strength, coordination, and confidence. Some need harnesses to practice walking safely. Others start with short sessions on treadmills before returning to normal motion. This process can take weeks or months, and it offers a preview of what humans might face on Mars or other worlds where gravity is different. Relearning to walk is not just physical, it is emotional, a reminder that our bodies are shaped and reshaped by the worlds we inhabit. Mars has storms that can last for months. Mars is a dry, cold world, but its atmosphere is full of movement. Winds can whip across the planet at speeds high enough to lift fine dust into enormous storms. These storms can start in a single region and slowly spread until they cover the entire planet. During these events, Mars becomes a hazy, muted sphere, with sunlight reduced to a faint glow even at midday. The dust can linger in the air for months, clogging equipment, blocking solar power, and coating every exposed surface. During a global dust storm, the temperature swings and pressure shifts can affect everything from landers to future habitats. The dust itself is sharp and dangerous, containing toxic chemicals that can damage lungs and electronics. Living on Mars will require shelters strong enough to withstand the storm and systems that can function without sunlight for long periods. On a planet of red dust, the weather becomes a force that can reshape every mission plan. Every mission to deep space creates new medical mysteries. Space medicine is still in its early years. Doctors know how microgravity affects bones and muscles, but long-term effects on the heart, nervous system, vision, and mental health are still being discovered. Fluid shifting in the body can change pressure in the eyes, causing blurry sight. The immune system may weaken, allowing dormant viruses to reactivate. The brain may reorganize its balance circuits, leading to strange dreams or motion confusion. Even the way wounds heal could change, as cells behave differently in microgravity. Each new mission becomes a human experiment, revealing hidden parts of biology shaped by Earth's gravity. Future explorers will face these mysteries with every step farther from home. The more we learn, the more we realize how deeply life on Earth is designed for Earth itself. To thrive in deep space, we may have to rethink everything about the human body. Spacecraft must shield against micrometeorites traveling faster than bullets. Space is filled with tiny fragments of rock and metal left over from the birth of planets or broken off in collisions. These micrometeorites are often smaller than a grain of sand, but they can travel tens of thousands of kilometers per hour. At those speeds, even a tiny fragment could punch a hole through metal, glass, or the fabric of a spacesuit. To survive, spacecraft are built with layered armor designed to break up particles before they hit the inner hull. Spacesuits have reinforced platting, and external tanks or modules sometimes double as shields. Engineers track large debris, but micrometeorites are too small to detect, so every mission carries the constant risk of an invisible impact. Even the International Space Station has small craters and scratches from past collisions. Traveling through space is like crossing a cosmic shooting gallery, where every spark becomes a threat. Protection becomes a delicate balance of weight, material, and design. You can watch Earth's weather systems from space. From orbit, the Earth is a living painting. Storms swirl across oceans like spinning galaxies. Clouds stretch across continents in delicate strands, and lightning flashes through storms in silent bursts of light. Astronauts can see entire hurricanes forming and moving below them, watch rain shadows crawl across deserts, and witness the soft glow of city lights beneath layers of cloud. Weather becomes global, not local, a dance of air and water shaped by sunlight and rotation. This view helps scientists understand how storms grow, how climate shifts, and how oceans and atmosphere exchange heat. It also reminds astronauts of the fragility of the world below. Every storm, every shadow, every river of cloud is part of a single, interconnected system that supports life. From above, Earth is not just a planet. It is a home wrapped in air and water, alive with motion and color. Every spacecraft has a maximum safe radiation dose. The universe is filled with invisible radiation from stars, galaxies, and high-energy particles. Earth's atmosphere and magnetic field block most of it, but in space, spacecraft are constantly exposed. Each mission calculates the total amount of radiation its crew and electronics can safely endure. There are limits based on age, gender, and length of exposure. If a spacecraft stays too long in a high radiation zone, or if a solar storm erupts unexpectedly, the risk rises sharply. Radiation can damage DNA, weaken immune defenses, and increase cancer risk. For electronics, it can corrupt memory, destroy circuits, or shut down systems permanently. Engineers design shielding, but the more protection added, the heavier the spacecraft becomes. Balancing safety, weight, and mission goals is a constant challenge. In space, the invisible becomes deadly, and every journey is measured not just in distance, but in dosage. Sound does not travel in space, but vibrations do. In the deep vacuum of space, there is no air or gas to carry sound waves, which means a scream, a roar, or an explosion would be completely silent to the human ear. Yet the universe is not entirely mute. Vibrations can travel through solid structures, allowing astronauts inside spacecraft or space stations to hear the hum of machinery, the creak of metal expanding in sunlight, or the gentle knock of someone tapping. Or from another module. In space, sound is not a wave in the air, but a vibration in a shared surface, felt as much as heard. Even instruments that measure gravitational waves translate distant cosmic events into low, eerie tones humans can perceive through speakers. If you were outside a spaceship in a vacuum, speaking to someone through a helmet speaker, you would only hear them through electrical communication, not through air. The silence of space is profound, but sound still exists in solid connections and through technology. It is silence broken only by the hum of life support systems, the buzz of your own suit, and the steady sound of your own breathing within your helmet. The first footprints on the moon are still there. When the Apollo astronauts stepped onto the moon in 1969, they left behind boot prints, tool marks, and even tire tracks from their lunar rover. The moon has no wind, no rain, and almost no geological activity to disturb these impressions. Without erosion, those footprints may last for millions of years. Even meteoroid impacts are rare enough that many marks remain completely untouched. These trails across the dust are like scattered fossils of human exploration, frozen in time. They tell a story of a few brief days when humans visited another world, leaving behind not just scientific instruments and flags, but the traces of footsteps from a world far away. Future explorers may someday walk the same ground, standing beside a footprint that has not shifted since the moment it was made. The scene is both beautiful and haunting, a reminder that once we touch a world without weather, we leave a mark that time forgets to erase. A tiny hole in a spaceship can be catastrophic. Every spacecraft is built like a sealed container, holding back the vacuum of space with layers of metal, insulation, pipes, and wiring. A hole no bigger than a grain of sand can start a leak that drains air rapidly, depressurizing the entire cabin. This is not a dramatic explosion like in movies, but a silent, steady escape that can go unnoticed until alarms detect falling pressure. Micrometeorites or fragments of space debris can punch tiny holes through metal walls, causing a gradual but deadly leak. Astronauts are trained to locate and patch breaches using special sealants and emergency covers. Even a drill error during construction or repair can cause a breach. The inside of a spacecraft is a bubble of Earth surrounded by nothingness. A single failure in that surface can turn the familiar air into a dwindling resource. Engineers layer walls, add alarms, and build in safety redundancy. But the threat remains. In space, the line between life and vacuum is often thinner than a sheet of paper. Astronaut suits have real gold in the visors. The helmet visors that protect astronauts during spacewalks are coated with a thin layer of gold, so thin it can barely be seen. Gold is a powerful reflector of infrared radiation, blocking dangerous sunlight that could scorch skin or damage eyes. Unlike many metals, gold does not tarnish or react with oxygen, making it long-lasting even under extreme conditions. The gold layer keeps astronauts cool in the blazing sunlight of space, where temperatures can rise quickly without atmospheric shielding. It also protects them from ultraviolet rays that would be filtered naturally by Earth's atmosphere. The visor includes several layers, each with a purpose. But the gold is the shield that stands between the astronaut and the raw, unfiltered glare of a star. It is a reminder that even the most advanced technology leans on ancient materials. In the emptiness of space, something as simple and symbolic as gold becomes a tool of survival. We have sent bacteria to space to see if life can survive. Scientists have launched bacterial samples into orbit, and even beyond, to test whether life can endure the stresses of space. Some bacteria, exposed directly to vacuum, radiation, and temperature extremes, survive for years by going dormant. Others thrive in microgravity, multiplying faster or developing stronger resistance to antibiotics. One experiment placed bacteria on the exterior of the International Space Station for long periods, and they returned to Earth still alive. These findings raise fascinating questions about the origins of life. Could primitive organisms have traveled between planets on meteorites, seeding worlds with biology? Studying bacteria in space also helps doctors understand how human health might change during long missions. Microbes evolve quickly and can adapt faster than human cells to the strange conditions of space. The results show that life is tougher and more adaptable than we once believed, and that space may not be as empty of biology as it seems. Some materials become stronger in zero gravity. On Earth, when molten metal or crystallized materials solidify, gravity pulls on their atoms and molecules, sometimes creating imperfections or uneven density. In the weightlessness of space, materials can form more cleanly, with fewer defects. Researchers have grown ultra-pure crystals in orbit, testing them for use in medical equipment, electronics, and even future spacecraft parts. Some alloys develop new properties when mixed in space. The lack of sedimentation or convection during solidification makes microgravity a kind of perfect laboratory for studying matter. Imagine building engines or computer parts with materials so smooth and flawless that they outperform anything made on Earth. For now, these experiments are small-scale and experimental, but they hint at a future where manufacturing in orbit could produce goods impossible to make under gravity. Even the simplest metal bar might hold secrets when forged among the stars. It takes months to mentally prepare for a space mission. Spaceflight is not just a physical challenge, it is a psychological transformation. Astronauts spend years learning how to solve technical problems, operate machinery, and survive emergencies. But the emotional preparation is just as important. Living in a confined space with a small group of people, far from home, without fresh air or sunlight, brings stress unlike any on Earth. Astronauts train in isolation chambers, underwater habitats, and remote environments to rehearse calm and emotional resilience. They meet with psychologists, practice mindfulness, and learn strategies for dealing with fear, boredom, and uncertainty. Even the sight of Earth from orbit can trigger overwhelming feelings of awe, loneliness, or responsibility. The mental journey to space begins long before liftoff. It requires shaping the mind to embrace silence, danger, and wonder without losing focus. The human spirit must be as strong as the rocket that carries it. Astronauts must learn to cry without gravity. Weeping in space does not look like it does on Earth. Tears do not roll down cheeks or drop onto the ground. They gather into shimmering globes, clinging to the eyelids until they overflow, spreading across the face or floating away. Even the act of crying can feel different, because emotions are heightened by stress and isolation. Astronauts must learn to wipe tears gently, using tools or cloths that catch the droplets before they drift into equipment. Tears can even cause discomfort if they stick to eyes or eyelashes, blurring vision. Medical staff discuss emotional triggers and healthy coping strategies before each mission. In the end, crying in space becomes not just a physical act, but a reminder of human vulnerability in an environment made for machines. Even in orbit, emotions are weightless, but not less real. The vacuum of space can boil blood. If a person were exposed to the vacuum of space without protection, the lack of pressure would cause bodily fluids to boil instantly, even at normal body temperature. The skin and blood vessels would hold for a short time, but gases in the bloodstream would expand and oxygen would escape from the lungs. A person would lose consciousness in seconds, not from freezing or suffocation, but from oxygen loss and internal pressure imbalance. Contrary to movies, the body does not explode, but it suffers rapid and irreversible damage. This is why spacesuits are pressurized like small spacecraft, creating an internal environment that mimics Earth conditions. Every layer of the suit protects against radiation, cold, heat, and the deadly vacuum. In space, the greatest threat is not just the cold, it is the absence of anything at all. The void itself can unravel life in a heartbeat. Landing on Mars is like trying to stop a car on a frozen pond. Mars has an atmosphere, but it is too thin to slow a spacecraft the way Earth's air does. Rockets alone cannot slow the descent enough without using enormous amounts of fuel. Parachutes help, but they must unfold perfectly in an atmosphere with less than 1% of Earth's density. The surface offers no dense air to brake against, and dust storms can obscure ground sensors. Spacecraft arrive at incredible speeds and have only minutes to slow down, steer, avoid rocks, and touch down safely. The process has been compared to trying to park a speeding vehicle on ice with worn-out brakes. Engineers use airbags, retro-rockets, sky cranes, and heat shields, testing each configuration again and again. Even then, some missions fail. The challenge of landing on Mars is one of the greatest obstacles to human travel in the solar system. Success is possible, but every attempt is a leap between risk and reward, written in fire and dust. There is no privacy in space. Life aboard a spacecraft is lived in tight quarters, with shared air, shared routines, and shared spaces that leave almost no room for solitude. The International Space Station has small sleeping pods, each about the size of a closet, where astronauts can zip themselves in and rest. But even then, they hear the hum of machinery and the muffled movements of others. Conversations can be overheard unintentionally, and cameras and sensors are almost always active for safety and mission control. Bathroom facilities are shared and only partially enclosed. Every message sent home is monitored for technical quality and sometimes delayed for review. Privacy becomes less about being alone and more about managing thoughts and emotions within close company. Astronauts train for this, learning how to balance personal needs with the mission's demands. In space, even a moment of quiet reflection becomes a small victory, earned in the midst of constant togetherness. The closest thing to a shower in space is a damp towel. There are no flowing streams or droplets drifting in the air when it comes time to get clean in orbit. Instead, astronauts rely on rinseless soap, water pouches, and absorbent towels to wipe their bodies. A small amount of water is squeezed from a pouch, massaged into the skin, and wiped away. Hair is washed with Uranus shampoo, combed through, and dried with suction fans. The process takes time and care, since water behaves unpredictably in microgravity, forming wandering spheres that can stick to surfaces or drift into equipment. Even after cleaning, astronauts may not feel entirely refreshed. They adjust by grooming more often, or switching to specialized clothing designed to resist odor and bacteria. The absence of a shower is more than an inconvenience. It is a reminder of the everyday luxuries Earth provides without thought. Personal care in space is not just hygiene, it is a moment of reclaiming comfort in an environment that offers none. Astronauts do experiments while floating. Every astronaut is also a scientist, working on experiments that explore everything from how cells divide in zero gravity to how tiny flames burn in air-free chambers. Because there is no up or down, equipment must be strapped in place or held steady by gloves and restraints. Liquids behave strangely, sometimes sticking to tools or pooling in unexpected shapes. However, microgravity allows unique studies that cannot be done on Earth, such as watching protein crystals grow without collapsing, or testing how water and oil mix when they are weightless. Astronauts become dexterous and inventive, mastering tasks like assembling miniature labs in mid-air or capturing free-floating samples without spilling them. Every experiment adds to our knowledge of biology, chemistry, physics, or engineering, knowledge that helps design safer spacecraft, more resilient medicines, and techniques for living beyond Earth. Even the simplest act, like stirring, becomes a scientific challenge in a world without gravity. Spacecraft windows must be replaced regularly due to micrometeoroid damage. Windows in space are not fragile panes of glass, but thick, layered structures made of polycarbonate and fused silica. Even so, they face constant onslaughts from micrometeoroids, tiny particles of dust and rock traveling faster than bullets. These impacts leave pits and scratches that scatter light, distort vision, and weaken the material. Space stations track incoming debris and rotate windows away from higher-risk directions when possible. Some windows have removable panels or protective shutters, while others are simply replaced once they reach a certain level of damage. Astronauts often take photos through the clearest sections, knowing that every view will eventually wear down. The ability to look out at Earth or the stars is one of the greatest privileges of life in space, but it is also a reminder of the risks outside. Each mark on a window is a signature of collision, a tiny scar from the universe itself. Mars has seasons, but they are twice as long as Earth's. Mars orbits the Sun more slowly than Earth does, taking nearly 2 Earth years to complete a single journey. As a result, each Martian season lasts about twice as long as its earthly equivalent. Winters are long and frigid, reaching temperatures far below what we experience on Earth, and summers are mild but dusty, sometimes accompanied by storms that envelop the entire planet. Because Mars has a tilted axis similar to Earth's, it experiences changing sunlight patterns that shift the weather throughout the year. Ice caps grow and retreat, carbon dioxide freezes out of the atmosphere, and winds carve sand dunes into new shapes. Future settlers on Mars will have to adapt not only to the freezing nights and thin air, but also to a calendar where seasons feel familiar but stretched, as if time itself has slowed down to match the rhythms of a distant cane. World. You can see entire continents pass beneath you every 90 minutes. From low Earth orbit, the International Space Station completes one full circle of the globe in about 90 minutes, traveling faster than any commercial jet could ever dream. Through its wide windows, astronauts watch oceans, mountains, cities, and cloud systems pass beneath them like a moving map. Sunrises and sunsets come every 45 minutes, painting the atmosphere in thin lines of gold and indigo. Rivers look like silver threads, and at night, lightning flashes across entire storm systems like glowing veins. Borders between countries disappear into landscapes, reminding observers that Earth is one shared sphere, fragile and whole. This view can change a person's sense of place forever. Astronauts often talk about the overview effect, a shifting consciousness that comes from seeing Earth as a single, interconnected home, drifting through space with no dividing lines except the ones we imagine. Spacecraft can charge themselves with electricity just by moving. As spacecraft travel through charged particles in Earth's magnetic field, they build up static electricity from friction with the ionized gases and dust in space. This effect can create dangerous electrical imbalances between different parts of the spacecraft, leading to sparks or shocks that can disrupt electronics or cause fires. Engineers design systems that allow excess charge to bleed off safely or redistribute evenly across the surface. Some spacecraft even use this effect to collect power, though it requires careful control. The phenomenon, called electrostatic charging, is a constant challenge, especially for satellites and probes that venture through high radiation zones. In the vacuum of space, there is no air to carry electricity away, so every static spark becomes a problem to solve. Spaceflight turns even silence and emptiness into a source of energy and of risk. Spacesuits weigh more than an astronaut on Earth. A fully equipped spacesuit with its metal rings, reinforced layers, pressure systems, communication devices, oxygen tanks, and cooling tubes weighs more than 100 kilograms on Earth, often more than the astronaut wearing it. The weight does not matter in microgravity, where the suit floats just like the person inside it. But on Earth, training in the suit is exhausting and sometimes painful, requiring underwater practice or weighted harnesses to simulate weightlessness. Every suit is custom fit for the wearer, molded to their measurements and designed for the specific mission. Even the gloves alone are incredibly complex, built to provide both protection and precision in the harshest environment imaginable. A spacesuit is a spacecraft in clothing form, carrying life support, shielding, mobility, and communication. It is heavy in body, but priceless in function, a wearable sanctuary built for the vacuum outside. There is a growing debate about who owns space. Space was once considered a frontier with no borders, protected by treaties that forbid any one country or company from claiming celestial territories. But modern missions have raised new questions. Private companies want to mine asteroids for minerals. Nations are planning permanent bases on the moon. Satellites are filling up orbits at unprecedented rates. Who decides where one mission's rights end and another's begin? What happens if a company lands on an asteroid first, or plants a flag on a crater rich in ice? Laws struggle to keep up with technology, leaving space in a legal twilight where ideals, economics, and diplomacy converge. Future generations may need new treaties that balance exploration, commerce, and protection of the shared sky. The cosmos may seem endless, but human ambition is reaching every corner faster than our rules can follow. Even breathing in space is a technology problem. On Earth, breathing is effortless, an invisible exchange between body and atmosphere. In space, every breath must be manufactured, filtered, and recycled. Oxygen is delivered in pure form through tanks or generated from electrolysis of water. Carbon dioxide must be scrubbed from the air using chemical filters that trap gas molecules before they build up to toxic levels. Humidity must be controlled to prevent mold, rust, or equipment failure. Every system depends on electricity, materials science, and fail-safe design. If even one link in the chain breaks, if a filter clogs or a pump fails, the atmosphere can become dangerous within minutes. Breathing becomes a process, not a reflex. Every inhale is a reminder of how strange life is outside the cradle of Earth, where air is not a gift but a machine we must build and protect. Robots may build the first homes on Mars. Before humans ever step onto Martian soil to stay, robots might arrive years ahead of them to construct the first shelters. These robotic builders could use the planet's own soil, called regolith, mixed with special binders to 3D print protective walls and habitats. This approach avoids the need to transport millions of kilograms of building materials from Earth. Robots may also dig trenches for wiring, assemble solar arrays, and set up life support systems for incoming crews. Their presence turns the lonely planet into a quiet worksite, preparing a safe foothold long before the first human breathes Martian air. This strategy means astronauts could land with ready-made homes, power, and pressurization, instead of scrambling to build everything on arrival. For now, robotic construction is being tested in deserts, Antarctica, and other isolation zones on Earth. If it works, the first home ever built on Mars will not be built by human hands, but by machines sent to make life possible where no life yet exists. Water behaves like living jelly in space. In zero gravity, water transforms from a flowing liquid into a floating wonder. It forms spheres that drift through the cabin, wobbling and stretching like tiny planets of shimmering glass. A gentle touch can break one into smaller globes, each quivering with surface tension. Water clings to fingers, cheeks, and equipment panels, unless wiped away with great care. Astronauts cannot pour water or even drink from open cups. They sip from sealed pouches so droplets do not escape into machinery. Even washing becomes a careful act of trapping and wiping. This jelly-like behavior appears because gravity no longer pulls the water downward. Surface tension becomes the leading force, turning every drop into a squishy shape that almost seems alive. In this strange version of physics, water reminds astronauts that even the most familiar things behave like something new the moment gravity lets go. Most astronauts bring a personal item to space. Even in the ultra-efficient scheduled world of space missions, astronauts are given room for a small personal item. These keepsakes may be tiny toys from childhood, a family photo, a national flag, a wedding ring, or something deeply symbolic. The item fits into a small pouch packed with care among tools and equipment. Once in orbit, it becomes a comforting reminder of the world below, a touchpoint of grounding in an environment of machines and silence. Many astronauts choose objects that represent people or memories they do not want to leave behind. When they return home, the item itself becomes a relic of spaceflight, forever changed by its journey beyond Earth. A simple keepsake becomes a time capsule of emotion, memory, and a view few humans will ever know. You can watch a sunrise every 90 minutes in orbit. Aboard the International Space Station, astronauts circle the globe once every hour and a half, watching the sun rise and set around 16 times each Earth day. As the station approaches the edge of light, a thin arc of color appears along Earth's horizon, shifting from deep indigo to orange, then bright white. The blue glow of Earth's atmosphere seems almost unreal when seen from above. 45 minutes later, the sun disappears again behind the planet, and the surface below falls into shadow, where city lights sparkle in constellations of their own. This rapid cycle of day and night creates a new rhythm of time, not ruled by clocks or calendars, but by the turning of Earth beneath the silent spacecraft. Sunlight never settles, and night never lasts long. It is a place where sunrise is almost always just a few minutes away. Every mission leaves behind a trail of forgotten artifacts. Across the Moon, Mars, and even the empty expanses of space, humanity has left behind a scattered collection of leftovers. On the Moon, there are footprints, tools, rover tracks, flags, and even a family portrait left by an Apollo astronaut. Mars is home to heat shields, parachutes, landers, and the quiet tracks of rovers making their way across ancient soil. In Earth orbit, old satellites drift alongside screws, gloves, paint flakes, and even a lost tool bag. Some objects were placed deliberately, while others were left because they were no longer needed or became too risky to bring home. These space relics are the accidental archaeology of exploration, reminders that every journey changes not only the traveler, but the place they visit. One day, future explorers may collect and study them as the first artifacts of humans leaving their home world behind. A spaceship must carry fire, air, food, water, and gravity. A spaceship is a self-contained ecosystem, built to support life in a place with no air, no soil, no weather, and no help. It must generate breathable oxygen, filter harmful carbon dioxide, and control temperature and humidity. Food must be stored in sealed packages for months or years at a time, still safe to eat when opened. Water must be recycled endlessly, since every drop is precious. Fire must exist in controlled systems for warmth or energy, yet any spark must be prevented from spreading. Since gravity does not exist in space, the vessel must simulate it or compensate for its absence, often using exercise machines or rotating designs to keep muscles and bones from decaying. The ship becomes a tiny Earth, held together by technology instead of nature. Every breath and every bite depend on machines working perfectly, because there is nothing outside but silence and vacuum. You can hear the space station creak and moan. To astronauts, the International Space Station is never truly quiet. Air circulates through ducts, fans hum around the clock, and motors adjust position or pressure. As the station orbits from sunlight into shadow, its metal walls expand and contract, making soft pops, groans, and clicks. The sounds are like those of an old sailing ship, shifting on waves no one can see. Even the vibrations of nearby modules can be felt through the structure, reminding crew members that they are not alone. Earplugs are often used for sleep, and white noise machines can help soften the background sounds. These noises become part of daily life, signals that the station is alive and working. They are also small comforts, a reminder that silence in space means something has gone wrong. Spacesuits must be pressurized like balloons. A spacesuit is not just a layer of protective material. It must hold internal pressure to keep the astronaut's body from expanding or being harmed by the vacuum outside. The suit inflates to a safe level, pushing against the skin just as the air around us does on Earth. This pressure makes the suit stiff, so every movement takes effort. Bending arms, gripping tools, or turning the head feels like working inside a balloon that pushes back each time you flex. Engineers solve this with rotating joints, layered materials, and temperature control systems that help regulate the forces inside. The suit also provides oxygen, removes carbon dioxide, filters radiation, and protects against extreme temperatures and tiny high-speed particles. Without pressurization, the astronaut's body would suffer quickly, even if the air was breathable. The suit is life itself, zipped and sealed around a single human floating in emptiness. Venus is a deadlier destination than Mars. Mars may be cold and barren, but compared to Venus, it is almost welcoming. Venus is a world where temperatures reach nearly 500 degrees Celsius, hot enough to melt metal. The atmosphere is thick with carbon dioxide and sulfuric acid clouds, pressing down with a force 90 times stronger than Earth's air. Landing on Venus is like diving into a boiling, toxic ocean of heat and pressure. Even the most advanced robotic landers have survived for only a few hours before being crushed or cooked. Yet Venus was once more like Earth, with oceans and possibly a mild climate. Something changed over millions of years, trapping heat and transforming the planet into a furnace. Studying Venus helps us understand how planets evolve and why Earth is still habitable. For now, it is a place we visit only at a distance, its dangers too great for human feet to touch its soil. Space farming could make us a multi-planet species. To live on other worlds or in long-term space habitats, humans will need food that does not depend on Earth. That means growing plants in places with no soil, no wind, and artificial light. On the International Space Station, astronauts have already grown lettuce, radishes, and even flowers using hydroponic systems and LED lamps. These plants not only provide fresh nutrients, but also recycle air by releasing oxygen and absorbing carbon dioxide. Future farms on Mars or lunar bases might use water extracted from ice deposits, composted waste, and nutrient gels instead of dirt. Plants in space may even need to adapt, growing with different shapes or structures in low gravity. Farming off-world gives us something precious, a reminder of Earth's life in a sterile environment, and a tool that could make it possible for humans to live far beyond the confines of one planet. Future space habitats might spin to create gravity. One of the most complicated problems in living away from Earth is the lack of gravity. Without it, bones weaken, muscles shrink, and even the heart changes shape. Instead of fighting this with endless workouts, future space engineers may create artificial gravity by building enormous rotating habitats. These structures could spin slowly but steadily, causing everything inside to be pushed outward, just like water in a turning bucket. This would recreate the sensation of gravity by using centrifugal force instead of relying on a planet. Designs include gigantic rings in orbit, spinning space stations, or even rotating cities built near the Moon or Mars. People inside would be able to walk, sleep, and work on curved inner surfaces that feel completely flat underfoot. Growing food, keeping pets, and raising children would all become easier in a world with simulated gravity. If it works, these spinning homes could become the first real places where humans live permanently in space. Not just visit. It may even become normal for whole generations to grow up inside worlds that turn slowly in the heavens, creating their own version of down, sky, and ground. Space travelers must learn to live with constant danger. Living in space means accepting that almost everything around you can become deadly in a moment. There are no oceans or forests out the window, only a vacuum so empty and cold that it would boil the moisture in human lungs and eyes instantly. A single broken seal, fire spar, or burst pipe could fill a spacecraft with smoke or poison. Impossible weather, solar storms, and unstoppable debris race silently through the void. Even sleep must be done carefully, strapped into a wall so you do not drift away and bump into equipment. Every astronaut is trained not just for science, but for survival, repair, emergency medicine, and mechanical skill. They must learn to live calmly in places where there are no exits, no outside help, and no second chances. Yet with practice, this danger becomes a part of the background, like the wind or rain back on Earth. Space travelers form a kind of trust with their ship, their training, and one another. That quiet trust is what keeps them alive, hour after hour, as they work among forces that do not care whether a human lives or not. Human bodies may evolve differently on other planets. If humans build colonies on Mars or other worlds and begin raising children there, natural evolution may start working along completely new paths. Lower gravity could change height, posture, and the strength needed to stand or move. Bones might grow longer or lighter. Muscles in the legs and back might weaken over generations. Children raised on Mars might feel heavy and slow if brought back to Earth. Their hearts could pump differently. Their eyes might change sensitivity under new levels of sunlight and radiation. If people start living beneath domes, in caves, or in low light, skin color could change to adapt to new levels of ultraviolet rays. Even senses such as balance may become tuned to places where gravity does not point the same way. Over centuries, these differences could grow larger and more permanent, just as human populations once adapted differently in deserts, mountains, and icy forests. The real question is whether humans across different planets remain one species, or whether our descendants might begin to look and live in ways that no longer match where we came from. Space will not just change our technology, it will change us. Dust on the moon smells like gunpowder. When Apollo astronauts came back into their lunar module after walking on the moon, they discovered that the fine grey dust coating their suits had a strange scent that reminded them of burnt gunpowder. No one smelled it on the moon itself, since space has no air, but once helmets came off and the dust met oxygen, the smell released. Lunar dust is razor sharp, formed by countless tiny impacts from meteoroids over billions of years. It has never been touched by wind or water, so its edges are jagged and cling to anything that comes near. Once inside the cabin, it clung to skin and eyes, irritated lungs, and scratched equipment. The scent came from tiny chemical reactions between oxygen and elements bound inside the dust, such as iron and silicon. If humans ever return to live on the moon, this dust will be one of the biggest hazards. It could slice into machinery, scar lungs, or even block air filters in tiny but deadly amounts. The smell of gunpowder was only the first warning of how alien and dangerous even the ground beneath our boots can be on another world. A dead satellite can drift for centuries. When a satellite stops working, it does not fall back to Earth like a rock. If it is in a high enough orbit, it keeps circling the planet, silent and powerless, for decades or even centuries. There are thousands of these inactive machines above us, ranging from weather satellites to early communications devices. Some are carefully moved into a graveyard orbit to stay out of the way of active spacecraft. Others were abandoned before such rules existed and now pose collision risks. Even very tiny fragments, no larger than screws or paint chips, move faster than rifle bullets and can rip holes in solar panels or shatter delicate instruments. A small crash between two dead satellites could create clouds of fragments that crash into others, creating more fragments in a chain reaction. This is called the Kessler effect, and if it grows too rapid, it could make space travel difficult or even impossible for many years. Dead satellites drift like forgotten ghosts above all nations, waiting for the day we learn to clean up what we once launched without thinking of the future. Space mining could power civilizations. Some asteroids contain more platinum, nickel, gold, and rare metals than exist in all the mines of Earth. Others are filled with frozen water that can be turned into rocket fuel, air, or drinking supplies. If humans learn to mine space rocks, we could support entire space stations or planetary bases without needing constant resupply from Earth. One asteroid only a few hundred meters across could supply enough metal to build thousands of spacecraft. Water in deep space could allow ships to refill tanks between planets. Scientists are already mapping which asteroids contain useful materials and designing robots that could land, drill, and melt ore without any humans on site. Companies have even formed with plans to claim mining rights once international laws allow it. One day, space industry may not depend on Earth at all. Factories in orbit could build ships, solar farms, habitats, and satellites using metals harvested in vacuum. Space mining could become the fuel of interplanetary civilization, just as coal once fueled industry and oceans once fueled trade. Spacecraft must carry their own magnetic fields. Earth protects us from deadly solar radiation using its powerful magnetic field, which diverts high-speed particles away from the surface. But once a spacecraft travels far from Earth, that protection fades, and the full force of cosmic radiation begins to strike the hull and everyone inside. This radiation can damage electronics, break DNA, increase cancer risk, or even trigger hallucinations from particles entering the brain. One solution being researched is to give spacecraft their own magnetic fields, using coils of electric current or plasmas that mimic the shape of Earth's defense. These systems would surround the ship with an invisible bubble that pushes radiation aside, just as a shield of wind protects a flame from sparks. The challenge is building a field strong enough without using too much power. But if mastered, magnetic shielding could allow people to travel safely to Mars, Jupiter's moons, or the outer planets without being harmed by the invisible storm of particles flying through space every second. The first baby born on Mars will never be fully Earthling. If humans begin raising children on Mars, the very first child born there will not just be a milestone in science. It will be a turning point in the human story. A baby born in 1/3 of Earth's gravity will develop a heart that pumps differently, a spine that grows differently, and possibly new proportions of muscle and bone. Their body will form under a sky with different light, different pressure, and different chemistry. Their first language may have words for things that do not exist on Earth. Even their immune system may build itself around bacteria found only in colonies, not in forests, oceans, or farms. If this person grows up never setting foot on Earth, they may feel heavier and weaker when they finally visit. They will not be less human, but they will be the beginning of a new branch of human experience, shaped not by Earth's gravity and air, but by the raw and red horizon of another world. Astronauts see invisible light with special cameras. In space, sunlight contains more than visible colors. There is ultraviolet, infrared, and radiation that never reaches Earth's surface because our atmosphere blocks it. To study the universe, astronauts use special cameras that reveal these invisible forms of light. Through infrared cameras, they can see warm objects glowing even in total darkness. Through ultraviolet imaging, they can watch stars and galaxies burning with energies that no human eye can perceive. Astronauts can even track how much heat leaks from spacecraft panels, or how fast Earth's oceans release warmth at night. Some cameras reveal electrical storms at sea, glowing in ultraviolet light like hidden fire. These tools are not just scientific. They change the very idea of what is real, showing a world of colors and forces that humans never evolved to see. When astronauts look through these lenses, they witness a version of the universe that has always been there, waiting for technology to bring it into human sense. In space, you can only tell time by Earth. On Earth, time is marked by the rhythm of rising sun, sunsets, days, and seasons. In space, none of those exist unless you look down at the planet below. The International Space Station circles Earth every 90 minutes, which means the sun rises and sets 16 times every single day. Instead of using space-time, astronauts simulate Earth clocks so they know when to sleep, exercise, and run experiments. Mars has days that are slightly longer than Earth. The Moon has days that last nearly a month. Deep space has no days at all, only mission clocks that count hours since launch. Even the idea of a birthday becomes complicated when calendars have no physical meaning in vacuum. Time in space is not written by sunlight, shadows, or seasons. It exists only because humans carry it with them, like a memory of where we came from and where our minds still live. You can run around an entire asteroid in minutes. Many asteroids are no larger than a city block, and even the biggest are still tiny compared to moons or planets. On one of these small worlds, an astronaut in a spacesuit could literally run around the entire surface in just a few minutes. The reason is gravity. Asteroids are made of rock and metal, but most are too small to pull objects down with any real force. An adult might weigh only a few grams while standing on the ground. This week, gravity changes not only how a human stands or walks, but how they move. A gentle jump could send someone flying high above the surface before drifting slowly back down. A fast run could become a series of controlled leaps, almost like flying in slow motion. Astronauts would need magnetic boots or tethers to stay attached during exploration. They might also bounce instead of walk, carefully managing momentum so they do not throw themselves into space by accident. Exploring an asteroid is a reminder that in the universe, even movement depends on the size of the world beneath your feet. Future Mars settlers will need new calendars. When humans eventually live on Mars, they will no longer be able to use Earth's calendar to mark time. A day on Mars is longer than a day on Earth by about 40 minutes, and a Martian year is almost twice as long. Seasons are stretched. Sunlight changes differently. Even the length of a shadow at noon follows new rules. To make daily life practical, colonists will need clocks and calendars designed for the rhythms of a different planet. Work shifts, school schedules, planting cycles, and celebrations will all follow Martian sunrises and sunsets, not Earth's. Months could be based on the motions of the two tiny Martian moons, Phobos and Deimos. Year numbers might begin with the first landing of human settlers. Even birthdays might feel different, since a single year on Mars would be equal to almost 2 on Earth. Once people fully adapt to these rhythms,